So the next thing one more thing before we can do problems, that's contact forces. We're going to deal with contact forces a lot in this class. Normally, we're going to think of contact forces as joints because that's the way it's usually going to arise, like a thing's connected to a hinge here and a pin joint over here or something. But we're going to start out with just 3 different types of contact forces. This is for particle statics again. So the first one is a cable force. And a cable, well, let me just list them and then I'll go through how you do each one of these. So a cable force. The second one is a frictionless contact between bodies. And the third one is friction contact between bodies. Okay, so the first one is cable forces. And a cable always applies a force parallel to the cable and away from the chosen body. Okay, so let me show an example. So if you have a pulley attached to the ceiling and you have one mass hanging by a cable that goes over one side, call this body 2, and then body 1 is hanging from the same cable on the other side. Then a free body diagram of body 1. There's a weight force acting down. So that's M1 times G. And then the cable force is parallel to the cable where it connects to the body and away from the body, so that means it's this way. And a free body diagram of body 2. There's a weight force there, so I'll call that M2G. And then again, we have a force that's parallel to the cable, so it's either up or down, and it's away from the chosen body, so that way. And since it's the same cable just going over a pulley, that has the same force T. Any questions about that? And again, what it means that you represent that with a scalar variable T instead of a vector variable is that says we can represent that force with only one unknown. Okay. Everything except that magnitude can be calculated from what we're given because it's a known direction. Okay, the second one is frictionless contact. So if two objects push against each other without friction, and the force is perpendicular to the surface of contact, and toward the chosen body. So cable forces are away from the chosen body. Pushing forces are toward the chosen body. So for example, if you have two carts that are in contact and they're rolling along a surface, let's say this one's 5 kilograms and this one's 3 kilograms, and there's 100 Newton force pushing up the ramp. Well, this wouldn't be in equilibrium, but the free body diagram, you still do the same way. So what would those free body diagrams look like? For the 5 kilogram, you'd have a weight force. That's 5 times 9.81, so 49.05 newtons down. And then you'd have two pushing contacts. Where would those be? There's a normal force, yep. And whoops, you want to make it clear in your free body diagram when vectors are not parallel or perpendicular to each other. You should be able to tell from looking at the free body diagram whether they're parallel or whether they're perpendicular or neither. Okay, so I'll call this N5. Mm-hmm. Yeah. Right, but it will matter when we get to rigid bodies. So we're sort of setting up for that in a way. And then where's the other pushing contact? Oh, we're assuming frictionless for now. So the other one is from that other body. So there's a force R there. Yep. Right. And then free body diagram of the other cart. So there's the outline. And there's a weight force of 3 times 9.81, so 29.43 newtons. And then there's a pushing contact from the ground, I'll call that N3. And then there's a pushing contact from the 5 kilogram cart. So that force is perpendicular to the surface of contact toward the chosen body. And do we know the magnitude of that force? Oh, well, there's also 100, but that's not the one I'm talking about. Do we know the magnitude of this contact force? It's equal and opposite, so this is also R. That's Newton's third law. Any questions about that? Okay, and the last one is friction contact. Okay. So this is a pushing contact, but you also have friction. And in physics, when you dealt with friction, you did stuff where you have a coefficient of friction and you calculate the normal force, and then you use the normal force to figure out the friction. We don't have to do that here. And that's because since everything's in equilibrium, we can just calculate what the friction force has to be to keep it in equilibrium. So we're never going to really deal with coefficients of friction. Way later on we will for a couple of select things, but what we're going to do is just represent friction contact as a force vector with an unknown direction, a fully unknown force vector. So a force vector with an unknown direction. Okay, so this is the case where you're going to represent it by 3 components of a vector, and your vector variable, or your variable, is going to be a vector. So let me show an example of this. Okay, so let's say that you have a box on an incline. And the lower box has a mass of 2 kilograms. And the upper box has a mass of 1 kilogram. And let's say there's a horizontal force this way of 5 newtons on the top box, and a force vector parallel to the ground of 10 newtons on the bottom box. And we'll assume that there's friction between the 1 and the 2 and between the 2 and the ground. So free body diagram of the, let's do the 1 kilogram first. There's a weight force of 1 kilogram times 9.81. So 9.81 newtons down. There's the 5 question. Okay. There's a 5 Newton force horizontal. Well, we're only dealing with the one, so the 10 is not acting on the one. So that's not in here. But there is, yep, and we're not going to break it up into a normal force and a friction force. We're just going to treat it as an unknown force vector. So I'll just write it like this. Okay. And I'm going to use a notation that calls this the force vector on the one by the two. So this reflects the coordinate system that you use. So I'm assuming that we're just using the regular coordinate system. In physics, you use that rotated coordinate system because it makes it easier to represent it as a normal force and a friction force. But in this class, since we're not doing that anyways, there's no benefit to rotating the coordinate system. So we're just going to use the regular one. Okay, and then the 2 kilogram. So we have the downward weight force of 2 times 9.81, so 19.62. And down here, we have the force vector on the 2 by the incline. And then the last thing is, so there's contact at the top of the 2 kilogram box. So, and that's a friction contact, so it's going to be like this. And I'm going to write that as the force on the 2 by the 1. And what does Newton's third law say about the relationship between the force on 2 by 1 and the force on 1 by 2? Equal and opposite. So this is equal to negative F1, 2. Okay, so let me write down that notation. So notice this subscript notation, FAB is the force on body A by body B. And when we get to couples, it's going to be the same thing. So it would be a couple, capital M, A, B, and that's saying the couple on body A by body B. All right, so let's do a calculation. So let's say we have a ramp with a pulley at the corner. And there's a 5 kilogram cart over here that's connected to that cable. I can make that look better. And then hanging down from it Oh, sorry, I messed that up. You're gonna have to redraw this. So this needs to be a friction contact. So that box comes all the way down. And let's say that this is a 1 kilogram mass hanging from that cable. And we want to know what's the force vector that's applied to the 5 kilogram cart by the ramp. We need to know the angle that this ramp's at. Let's say it's 20 degrees with the horizontal. Okay, so you could, you look at this and think you want to do a free body diagram and use Newton's second law for the 5 kilogram cart, the 5 kilogram mass. It turns out if you did that first, you'd see that you couldn't calculate it yet. And then that would lead you to isolate the 1 kilogram mass. So I'm just going to do that first. Okay, so first I'm going to draw a free body diagram of the 1 kilogram mass. There's a weight force down of 1 times 9.81, so 9.81 newtons. And then there's a cable force that's parallel to the cable away from the body, T. And like everything in this class, we're going to assume that it's in equilibrium. It's not accelerating. By the way, it could be moving with a constant velocity, and the calculations are exactly the same. All we have to know is that it's not accelerating. And so now based on this, we'll go to Newton's second law. And so we have a downward force of 9.81 as a vector that's 0, negative 9.81. And we have an upward force of t, so that's 0t. And those have to add up to a 0 vector because there's no acceleration. The x equation doesn't give us anything useful, but the y equation says t is equal to 9.81. Okay. And so that's why we isolated this first, so we could calculate that cable tension. Okay, so now go to the free body diagram of the 2 kilogram. Is that what it is? 2? 5. So free body diagram of the 5 kilogram. So there's a weight force of 5 times 9.81, so 49.05. And there's a cable force parallel to the cable away from the body. And that force magnitude is T, which we just calculated. So yep, 9.81. Yep, and then we have, since this is a friction contact, we have an unknown force vector. I'll call that force on the 5 by the incline. So these two are easy to represent. The one that's takes a little working is, if here's our coordinate system, the cable force is this way with a magnitude of 9.81 and an angle of 20 degrees. So as a force vector, that's 9.81 times cosine of 20 and 9.81 times sine of 20. Could someone calculate those two components? Okay, so now we can go to Newton's second law. And we have 0, negative 49.05. Plus the force applied by the cable that we just calculated, 9.22, 3.36. Plus this unknown vector, you can write that as components x and y. And it's equal to 0, 0. And now that's just two separate equations, and you're calculating those F components. So F5I as a vector, the X component is negative 9.22. And the Y is, and so that's the force vector that the incline applies to the block.